Hello and welcome to this presentation on LED basics. In this presentation, we will look at a few topics in semiconductor lighting, such as light generation from a semiconductor material, LED chip technology, structure of an LED, creating white light in an LED package, and finally, some definitions of CCT and CRI. This graph shows the bandgap energies and corresponding wavelengths for two major semiconductor materials used for LEDs today. InGaN or indium gallium nitride is used for violet, blue and green LEDs, whereas InGalp or indium gallium aluminum phosphide is used for green, yellow, orange and red LEDs. The wavelength of light or its color is determined by the light's energy. The energy of a light particle emitted by an LED is equivalent to the bandgap of the semiconductor material used for the LED, which is an intrinsic feature of the semiconductor material used. Manufacturing an LED with a designated wavelength is all about engineering the semiconductor materials and their bandgaps. LEDs are semiconductor diodes or electronic devices that permit current to flow in only one direction. The diode is formed by bringing two slightly different materials together to form a p-n junction. In a p-n junction, the n side contains negative charge carriers, that is electrons, and the p side contains positive charge carriers, that is holes, which indicate the absence of electrons. When a forward voltage is applied to the p-n junction, electrons move from the n side towards the p side and holes move from the p side towards the n side and combine in the depletion zone between these regions. Some of these recombinations are radiative, in which energy is released in the form of light. The non-radiative recombinations occurring in the p-n junction result in heat being generated in the semiconductor material. The ratio of the radiative to non-radiative recombinations in the p-n junction determine the internal efficiency of the LED. Some of the light is lost within the semiconductor material due to effects such as total internal reflection, absorption and shadowing of contacts, resulting in only certain portion of the light exiting the package. This is the extraction efficiency of the LED. To improve the overall efficiency of the LED package, it is important to improve both the internal and the extraction efficiency of the LED. The first generation of power LEDs from Osram optosemiconductors were volume emitters with top and bottom contacts. These LED packages had a top emission of approximately 49%, resulting in almost 50% of the light lost within the package. Subsequent advances in semiconductor technology have resulted in improved efficiencies. Osram optosemiconductors thin film technology was the first surface emitter, which resulted in greater than 97% of the light being emitted from the top surface of the semiconductor chip. The thin film or thin-GaN technology is scalable with the chip size. The relative light output from the semiconductor chip increases almost linearly with the emitting area. This enables optimization of the usable lumens and cost with the appropriate chip size. To further improve the overall efficiency of the LED, optimization is required in all value-added steps, beginning from the substrate through the package. To fabricate an LED, we start with a substrate on which several epitaxial layers are grown atom by atom. After various chip processing steps, the entire wafer is diced into single chips, also known as dies. Finally, the small semiconductor chip is assembled into a package for mechanical protection and electrical, thermal and optical interface. To improve the overall efficiency of the LEDs, each of these manufacturing steps needs to be optimized. The image shows the construction of an LED package. Within a cavity of the LED is a semiconductor chip mounted onto a lead frame, which is housed in a pre-mold package. The lead frame acts as a thermal path to dissipate the heat from the semiconductor chip and also serves as the electrical and mechanical interface to the printed circuit board. A gold wire bond is used to connect the top side of the chip to the lead frame. The cavity is filled with epoxy resin and serves as a reflector to extract the maximum amount of light out of the package. This image depicts the construction of a high-powered LED package, the Golden Dragon Plus. The light source of the Golden Dragon Plus is a highly efficient semiconductor die mounted directly on an integrated heatsink in a pre-mold package. The silicon encapsulant in the package is formed into a lens which optimizes efficiency by allowing more of the generated light to be extracted from the package. Osram optosemiconductors offers a wide surface mount product portfolio featuring miniature, standard and high-powered LEDs. The miniature portfolio features low-powered LEDs with small package sizes. The The standard portfolio features the top LED, one of the longest running surface mount technology LED packages available on the market. The high power product portfolio features the Dragon and Oslon SSL family of products. Various LED parameters are used to quantify the performance of the LED. These include optical, thermal and electrical quantities. A monochromatic or single color LED emits light in a narrow spectral band. The spectral power distribution is a representation of the radiant power emitted by a light source as a function of wavelength. The semiconductor material used in an LED determines its wavelength or color of light. As mentioned earlier, InGaN and InGalp are the two primary semiconductor materials, and slight changes in the composition of these alloys changes the color of the emitted light. This image shows the various colors produced with different composition of alloys on a CIE 1931 color chart. Apart from monochromatic LEDs, white LEDs are used in a number of applications. One approach to generating white light utilizes a combination of three primary colors: red, green and blue LEDs. Another approach is to use blue and yellow LED chip together in a certain ratio in sum to produce white light. Third approach would be to use a blue chip and a yellow phosphor to generate white light, or by utilizing an ultraviolet LED to excite red, green and blue phosphors. The most widely used approach to create a white LED is to use a blue LED chip combined with a phosphor. The phosphor layer absorbs a portion of the blue light and emits light at longer wavelengths. The phosphor concentration defines how much of the blue light is upconverted. Volume conversion involves the dispensing of phosphor particles into the transparent molding material. An alternative method is chip level conversion, in which a phosphor layer is placed on top of the LED chip. The advantages of chip level conversion include better color homogeneity, higher luminance and less color variation over angle. In addition to white light, new color regions can be achieved by employing different phosphors. The correlated color temperature is the temperature at which a Planckian black-bodied radiator and an illumination source appear to match. It is usually specified in degrees Kelvin. The CCT for a light source gives a good indication of the lamp's general appearance, but does not give information on its spectral power distribution. Therefore, two lamps may appear to be the same color, but their effects on object colors can be quite different. Examples of CCT of some common light sources are shown in the figure on the right. This image shows the spectrum for various correlated color temperatures of white LEDs. By changing the phosphor content, it is possible to achieve different color temperatures of white light. The color rendering index, or CRI, is a measure of a light source's lighting quality. It's an index rating commonly used to represent how well a light source renders the colors of objects that it illuminates. For a CRI value of 100, the maximum value, the colors of objects can be expected to be seen as they would appear under an incandescent or daylight spectrum of the same correlated color temperature. 8 standard color samples are used for calculating CRI values. 6 additional color samples are used for evaluating rendering of saturated colors, skin tone and green foliage. Thank you for viewing this presentation by Osram Optos Semiconductors.